Hello class, it's Ms. Augustine, and we are ready to do some more notes for Chapter 4, Understanding Light and Energy. So we're going to talk today about the line emission spectrum of hydrogen. And it turns out that when an electric current is passed through a vacuum tube containing hydrogen gas, a pink glow is observed. So what you see right here is an example of a tube, a vacuum tube, and inside of it is hydrogen gas. And again, it's plugged into a source of electricity, so you're basically electrocuting the hydrogen gas. So the light that we see, if you pass it through a prism, and at the junior high you might have used these little spectroscopes. Basically, you look into one end of it, and then you're looking, and there's a prism, and then there's a little scale along here that kind of looks like this, and you can look at it and look at that tube of the glowing hydrogen gas and line up, there's a little slit in this, and line it up, and what you'll observe are 4 bands of lines that are the visible spectrum of hydrogen. So what's going on is we called that tube in the previous slide a gas discharge tube, and you're using the this little crude spectroscope here to line it up and look at that light. And what happens is it passes it through a prism, and then it gets separated out according to the different wavelengths. And so what you end up is with a line spectrum here, and this is giving a display very similar to the spectroscopes, and what it's doing is it's showing you the different wavelengths in nanometers. So the red line is around 656 nanometers, and the violet line is around 410 nanometers. So the 4 bands that we see are part of hydrogen's line emission spectrum. And again, here's another view of this. And 2 additional series of lines were also discovered that are not in the so-called visible region. So in the hydrogen spectrum, there are actually 3 groups of lines. The only one that's visible is the Balmer series, and I like to say to my classes that Balmer sounds like Palmer, and Mr. Palmer is usually in his office and walking through, so we see him. So the Balmer series is visible like Mr. Palmer. Then the other 2 series are the Lyman series, which is in the ultraviolet region, and the Paschen series, which is in the infrared region. Now, we're talking about this spectrum, and it's kind of a setup for next week after Thanksgiving. We will do a lab where we set up a whole bunch of those gas discharge tubes, and we'll use those little black spectroscopes, and we will record the various lines of a bunch of different elements, and then we'll pick out specific lines and we'll calculate their frequency, and then from the frequency we'll calculate their energy. So these are known as emission spectra, or singular emission spectrum. And again, what they're showing you is what's going on when the electrons, when the atoms absorb energy. So we talk about the lowest energy state of an atom is called its ground state. So when you think about being grounded, you are pretty steady, down to earth, not hype. And again, a state when an atom has a higher potential energy than its ground state is called an excited state. So if an atom is just hanging out and it's in a low energy state, kind of like hanging out on the couch, it's said to be in its ground state. And if it's in an excited energy state, it means it has higher energy. So you can think of the excited state as what I am like when I've had too much coffee. So again, these emission spectra that were observed by electrocuting various elements in vacuum tubes, and think back to Thomson and his cathode ray tube, same kind of deal, electrocuting atoms in their gaseous state elements and observing this glow. So the classic atomic theories predicted that hydrogen would emit a continuous range of frequencies, or a continuous spectrum. And so seeing just these little discrete lines kind of messed up people's brains a little bit. And so there were many attempts made to try to explain hydrogen's line emission spectrum. And again, that ultimately led to a new theory, which we call the quantum theory. So what's happening is hydrogen atoms in their ground state can absorb energy. When they absorb energy, their electrons jump up to these so-called excited states. And then when they relax back down again to their ground state, they release energy, and they release these photons of radiation. And remember, photons are these quantums or quanta of energy. So for the hydrogen spectrum, it's absorbing a specific amount of energy, and when it relaxes, it emits that same amount of energy, and we see that according to what wavelength is emitted that's associated with that energy, and again, we see that as a line. So the energy is emitted when the electron falls back down to a ground state, and that is associated with an emission of light. So Niels Bohr proposed that electrons have a fixed energy and that they move in fixed energy levels around the nucleus, which is why he said they don't fall into the nucleus. And in his model, he said that the energy levels that electrons can occupy are like the rungs of a ladder. They cannot be in between levels. They have to be at these specific orbits and need a specific amount of energy to move from one orbit to another. And again, the Bohr model is sometimes called the solar system model because he pictured the nucleus to be the sun and the electrons in their energy levels like planets orbiting around the sun. So Bohr's model of the hydrogen atom explained the observed lines that were seen for hydrogen, but it did not work well for explaining the spectra of atoms with more than one electron. So how do atoms produce light? I've said that atoms absorb and release photons as electrons move from one energy level to another. So here is a diagram, and what it's showing here is an atom, and here is a nucleus, and then these concentric rings are analogous to the various energy levels that an electron can occupy. And remembering that this is the Bohr model where we're picturing kind of a solar system with the nucleus being the sun. So what's happening is as light is coming in and the atom absorbs this energy, an electron can absorb that energy, and when it absorbs that energy, it actually jumps up to a higher energy level. So here, where's my arrow? Here it absorbs energy and it's going up to a higher energy level. Again, here's a different electron at a lower energy level, very close to the nucleus. It absorbs energy and leaps up to a higher energy level. So that is a so-called excited state. What eventually can happen, though, is then that electron eventually relaxes back down, and when it does, it emits that same amount of energy in terms of a photon. And again, here it relaxes down and it emits that same amount of energy. So the amount that it absorbed is the same amount that it released when it relaxes back down. So we talked a little bit about electrons as waves and electrons as particles, and light as waves and light as particles. So according to the quantum model, electrons behave as waves, and in 1924, Louis de Broglie suggested that electrons could be considered as waves that are confined around an atomic nucleus. So according to this, the electron waves could only exist at specific frequencies that correspond to these so-called quantized specific energies. And again, this is the same energies that we're talking about with the Bohr orbits, the Bohr energy levels. So his hypothesis was confirmed by experiments. So at this point, I thought it would be good for you to watch the Crash Course in Chemistry video, Episode 5, The Electron. Now, it's also available on YouTube, but I can't show you YouTube at school. So I'm going to suggest that you go using the computer, one of you log on to the computer and go to the Khan Academy, and you're going to be looking for Crash Course in Chemistry, which is on the Khan Academy, and it's Episode 5, The Electron.